kiddos, and welcome back. We're going to be moving into our discussion of now the two of the 4 quantum numbers. And what I'm going to do is we're going to fill in your notes on these and discuss your notes, and then I want to jump to a website to show you some really awesome visuals of what these look like. So remember, we talked about n was one quantum number, our energy level that gives distance and energy. And now what I want to look at is the subshell or the sub-levels. You've got to learn to interchange the word shell and level, and we use L. I try to kind of make it a little bit cursive so it doesn't look like an I or a 1 or something like that. Now, this is called the angular momentum quantum number, and since we have a nucleus here, electrons are somehow moving in a way that keeps them attracted, so there's angular motion. Now, we don't know how. They could be moving, weird like this. I'm just making this up, right? But some way that keeps them focused on that center. So also called a subshell, I mentioned that. Now this gives us the shape of the probability region, and this shows you the electrons. Now we're going to find again, I'm going to refresh your memory on this because I know it's been a while for many of you, that this links to the periodic table. And so all this information we'll be able to get directly from the periodic table by the time we're done. And so we have S, and then P, and then D, and then F, and then G, and then it would just go H, I, J, so forth. All right. Now, anything above F is an excited state, so far that we know of as scientists. So a way that a student made up to memorize this is stupid people die first, and then you go by the alphabet. And you see it goes 2, 6, 10, 14. Hopefully you're seeing that pattern of 4 there to find the number, the sub-level, the number of electrons that fit into each sub-level. All right, so now I'm going to show you pictures of these. You have some in your notes. Let me erase that. Sorry about that. Now, you have these pictures in your notes. I'm going to talk about the nodal plane here. I think we're going to see it a little bit better from the website. And I'm going to go over these radial distribution functions as well. Let me go ahead, though, and fill in these blanks for you. Nodes, and this is a node here, or you've got nodes, here through here, and here. Again, they'll be easier to see on the next video. It's the probability of finding the electron approaches 0. All right. And we're going to talk about electron density. So the greater the area under the curve, the greater the probability of finding the electron in that region. And we loosely call that an electron density. Higher electron density because there's a greater probability of finding an electron in those regions. Okay, now let's talk about the next quantum number. Okay, whoops. Arg. All right, this gives us, before we move on to M sub L, this gives us what sublevels are allowed for each energy level. So they're not all allowed. And when we talk about being allowed, we're talking about being physically reasonable or mathematically feasible. So if we're at energy level 1, all we can have is S. It's very close to the nucleus. You can't get too many electrons in there without adding too much repulsion. If you're at energy level 2, you can have S and P. Notice that the energy level number, that's how many sublevels you have. So energy level 4 can have 4 sublevels. Going stupid people die first. All right. And again, G's and H's are excited states. So hopefully that's coming back to you. All right. And we'll do some questions on this in a minute. I'm trying to get to that website quickly. So let's look at our orbital. Within each sublevel, there are orbitals. I hate that name. There's that implication in there that electrons orbit the nucleus. So I call it a misnomer, but I'm not queen of the world, so they're not going to listen to me on that one. Okay, this is where we finally have that 90% probability region. And this is called the magnetic quantum number. Whoops, that's a G, not a Q. Magnetic quantum number. And it gives us information on the orientation. So, orientation. So, L gives us the shape, and M sub L gives us how that shape is oriented in space. Okay? Now, let's see if there's any more blanks to fill in before we hop to this website. Nope, I don't want to talk about the spin quantum number. So let's go ahead and hop to the website that we have here. Okay. Now, if you Google, and if you want to see this website, if you Google winter orbital, you will see this website up here. Arg, Dina, that was my husband. I lost it. There we go. All right. If you Google winter orbital, you'll find this website. This shows a 1s orbital. And you notice that the 1s orbital is a sphere. And there's only one way to orient a sphere. And so for the 1s, M sub L, the number of orbitals is simply 1. And we would use a line there. So that would be an S. And we'd put 1s. So that 1 tells us what N is. The S tells us what L is, and the line tells us how many M sub L's. We're not going to assign numbers to those. We're just going to look at them simply. Now, if we're going to do that, we're going to build up that 2 electrons can go into each orbital. And S looks like a sphere. Now, remember I mentioned the radial distribution. That'd be like cutting it in half. And the radial distribution function would look something like that. Okay. Now, let's take a look at the 2s. Now, N is higher, so 2s should be bigger and further away from the nucleus. And it's not quite showing this to scale here, but it's like those Russian nesting dolls. This would be a sphere within a sphere. Now, we still have S, so this is 2s. So N is equal to 2, and L is equal to S. And we would use a single line because there's only one way to orient the sphere, and we're going to find that 2 electrons go in there. Hopefully these up arrows and down arrows are coming back to you from pre-AP chemistry. All right. Now, if I could draw the radial distribution function here, for this one, it's got, believe it or not, this finite probability of being near the nucleus. Then it hits a node, a 0 probability, and then it's got a greater probability of being found further away from the nucleus. Okay, so some tiny probability here, but repulsions get kind of big, so it's more likely to be found out here. And these regions represent the region in space where there's a 90% probability of finding an electron. So if we were to graph the y-axis here, we would be graphing psi squared, or the wave function squared, that 90% probability region. Now, let's go to the P. Now, if you remember from pre-AP chemistry, if this is coming back to you at all, the P sublevel is shaped like a dumbbell. So if we looked at this, this represents the whole P sublevel. So this is 2P sublevel. Within the 2P sublevel, there are 3 orbitals. And each orbital is going to hold 2 electrons. That's why the P sublevel can hold 6 electrons. And I'll show you radial distribution functions of that in your notes. I'm not going to try to draw that here. But let's go on and let me show you the 3p, just to show you that it gets a little bit more complicated, but the shapes are still the same. So if I go to the 3p, it still resembles a dumbbell, all right, but it becomes much, much more complicated. I want you to notice the similarities, though. We're still talking about the P sublevel. So for a P, this is 3P, so N is equal to 3, and L is P, all right? And the shape is still very much like that dumbbell or figure 8 type shape. It's a little more complicated, but it still has 3 orbitals in it. So that's because a dumbbell can be oriented in 3 different ways along the X, Y, and Z axes. And then again, we're going to end up putting in 6 electrons into that sublevel. That pink didn't show up very well, but I hope you get the idea. So remember, P gives us the shape. M sub L tells us that shape has 1, 2, 3 ways to be oriented in space. Now, again, if we jumped through these, the S is always a sphere, and there's always only one of them. So no matter how far it is from the nucleus, it's spheres. They're nestled spheres, but it's still the spherical shape. The P's are always dumbbell type shape, and a P sublevel dumbbell shape always has 3 orientations, hence 3 orbitals. Let's look at the D. The D is kind of this clover leaf shape, except for one weird one. So this is a D sublevel. So all of this represents a D sublevel. In this case, it's N equal 3 D sublevel. There are 5 ways to orient it. So there are 5 M sub L orbitals here. Being a little simplistic in our view, but hopefully you're following the path here. I'm just using lines for simplicity. Some people use boxes or circles for their M sub Ls. And we're going to find that the D holds 10 electrons. Always 2 per orbital. It doesn't matter if it's a D orbital or a P orbital or an S orbital. There's 2 electrons per orbital. And watch that notation, because questions will try to trip you up there. Now, let's take a look at the other D's. Again, it's always going to have that same overall shape, a little more complicated. This is the N equals 4 or 4D. There's still 5 orientations. So all D sublevels have 5 orientations or 5 orbitals associated with them, all the way up to 7D. I think these are so cool. They look like little spaceships, like they should be in the Jetsons or something like that, that cartoon, and we can fly from pod to pod. And, oh, well. Anyway, they're cool. So again, we're high up in energy level. This is 7. This is the electrons, by and large, are going to be much further from the nucleus. But D sublevels, 5 orbitals, 10 electrons. All right. Let's look at the F. The F is pretty cool. Hopefully you've seen the pattern of 1, 3, 5, 7. So there are 7 orientations for this funky F. Hopefully you would guess by now that G would have 9. Okay, so as you see those G's, there's 9 different ways to orient it in space. So there's 9 orbitals for G. Now, notice in this picture, we don't have 1p. It's too close to the nucleus, too much repulsion. We don't have 2d, too close to the nucleus, too much repulsion. We don't have a 4g, too much repulsion. All right, so I want you to kind of hopefully grasp that idea. I hope these pictures were a big help to you. So until I see you again, this is signing off.